we are now going to deal with the third and the fourth row. The discrete time Fourier series over here and the discrete time Fourier transform. I've drawn two arrows, one for DTFS, showing that I can perform DTFS in this way, and these are the equation. On the left is the analysis equation, on the right is the synthesis equation. What about discrete time Fourier transform? It shows that I can use DTFT for the aperiodic signal as well as the periodic signal. And now I'll write the equations over here, and I will explain the equations carefully as I'm writing it. So I've just drawn for you a periodic signal discrete time with period 5 samplers. I'm going to perform discrete time Fourier series on x of n. It basically will decompose x of n into all its harmonics, and the equation for analysis, Ck. So this is the analysis equation. There's nothing to write. It's all here. And what's the important take-home message? Okay, it's the first. The analysis of Fourier series means I know that our friend here is periodic. I will make use of the period n here. And n is made use of in here. I'm going to normalize it, and here. All right. Let us play with the range first. What about this n, small letter n? N equals to 0 to n minus 1. Okay, a single period. I'm going to take the single period. So if you look at this equation, taking a single period, x0 to x4, I'm going to multiply with a complex exponential. Of some frequency. And what is the frequency? And you observe that the frequency is this. Because I could have written it as E j omega n. And now you see that omega is the frequency of interest. And here the omega is this blue bracket here. Is equals to 2 pi over n k. All right. Now, if you look at 3 blue and 1 brown in the video, he will explain I am multiplying my signal against a complex exponential, and he's going to draw a very beautiful diagram to show what's happening here. In this particular example, all I'm going to tell you is I take a single period and I'm going to multiply my single period with a complex exponential of this frequency, and out comes a number. And this number will tell me how important is this complex exponential for this signal. How important in the idea of amplitude and phase. Out comes Ck, which is a complex number. Both telling me the amplitude as well as the phase. Okay? So once we have found all the Ck's, then we can reconstruct. Now, Ck's are interesting. Ck's are interesting because you realize that most of the time you think that K is 0, 1, 2, 3, and of course you have also realized in the continuous time Fourier analysis part, K can also be -1, -2, -3. And you will think that it will go on forever, but because we are now in discrete time, actually in our example, you will stop at n-1. After n-1, when you hit n, the frequency actually repeats. And there's no point to deal with n to 2n or 2n to 3n because it is the same as 0 to n minus 1. But we'll prove it as we go along. All right, so we have the analysis equation, and now we want to reconstruct. So now I want to see the synthesis equation. And synthesis equation means let us reconstruct x of n from C of k, and the answer is summation of k equals to 0 to k equals to n minus 1 ck e plus j 2 pi over n k n. Yep. So again, you see this is exactly this. The only change is the sign of the complex exponential. Ck is what we have found in the synthesis. And we are fine again. So we have shown you DTFS, the analysis, and the synthesis equation. And we'll visit this problem a few times, explaining in detail what all these little things means.